f of x is going to be x times e to the negative x squared. I'm going to think of this in terms of a physics application, but I'm also going to tell you that what I really have in mind is not so much a physics application, but a probability and statistics application. But it's easier to think about in terms of physics at first. So we'll think about it in terms of physics. If you use your calculator and graph this function over, say, the interval from 0 to 2, you'll get a graph that looks about like this. That's what the graph looks like. It turns out to have a maximum at 1 over square root of 2, which is about 0.7, and the maximum value is close to 0.4. I found it in the last class. It's close to 0.43. Anyway, that's just a little bit of context for what the graph looks like. More importantly, I want you to imagine this function to represent what you could call the linear mass density of a thin rod. Imagine a thin rod, maybe made out of metal or wood or something, lying on the x-axis from 0 to 2. How thin? Well, like wire thin. Maybe it really is a wire. Or maybe it's even a piece of hair or something. That thin rod or wire or piece of hair is so thin, it's effectively one-dimensional. Now, of course, it's really not one-dimensional. It's three-dimensional. But pretend it's one-dimensional. It's very, very thin. It's like the molecules are just lined up along a line. Why? It's because it makes the mathematical modeling simpler. That's why. It's easier to model in one dimension than in 3 dimensions. That's why we do it. And this is going to be a mass density. In certain units. Say a linear mass density. Linear mass density in, say, grams per centimeter. What does that mean? It's not constant. So that thin wire is not constant in density. In fact, where the function is higher, the density of the thin wire is higher. It's like the molecules are squished tighter together. It's highest near this location of 0.7. And since the density at 0.7 in location, that's in centimeters, is 0.43 grams per centimeter, that means if you get a scissors out or a wire cutter and cut off a tiny little chunk of that thin rod of length delta x near that point, you can approximate the mass of that thing without actually weighing it. Ignore the fact that mass and weight are different. Okay, you can approximate the mass of that without actually putting it on a scale and weighing it. The mass of tiny piece of wire would be approximately the mass density, 0.43 grams per centimeter, times the length delta x, which is in centimeters. You'd want to use consistent units. The centimeters would cancel, giving you 0.43 times delta x grams. And so, for example, if delta x is 0.1 centimeters, then the mass is approximately 0.043 grams, for example. So that's a mass of a tiny piece. What might we be interested in? We might be interested in the mass of the entire thin rod, the wire, without putting it on a scale. How do we find it? We could chop it into a bunch of pieces and do this kind of thing and then add the results, or better, since we've got this function, we can integrate it. Now, you might argue, who would ever do such a thing? who would ever, instead of just sticking that thin wire on a scale, would try to come up with a density function for it? That sounds like something only some nerd scientist would do. Okay, humor me. Okay, it's still a worthwhile thing to learn how to do for the sake of modeling. If for nothing else, okay, a real life example. So thin wires, maybe we don't care that much about. But what about asteroids flying around in space and rotating as they rotate? Can you figure out how that asteroid's going to move close up, like if you put a satellite near it, where the gravity is going to be affected? Okay, you need to learn these modeling skills so you can deal with complicated situations like that, where you can't actually make maybe some measurements that you might want to make. I don't know. Maybe that's not a good enough example, but that's the example that came into my mind right at that moment in time. So the total mass is actually going to be the integral of the mass density. The integral from 0 to 2 of x times e to the negative x squared. But that looks kind of complicated, doesn't it? I mean, last Friday, we saw that if you try to integrate a cosine of t squared, you got Fresnel c for your antiderivative. This e to the negative x squared are going to get Fresnel e. Can this be done by hand? Amazingly, it can be done by hand. It's easier than the integral of cosine of t squared. How do we do it by hand? Let's write it as an antiderivative first. Indefinite integral. Let's just try to find this integral first before we use the fundamental theorem of calculus. How do I do this? Here's how, and I'm not joking. Guess. Yeah, guess. Educated guessing. Will you be right? Not necessarily, but try. There are good guesses and there are bad guesses. A bad guess would be like cosine of x squared or something. Sine of x squared. Those would be bad guesses. Square root of x. It's got to involve e, right? The derivative of e to the x is e to the x. The integral of e to the x is e to the x plus c. Boy, I wish that were an e to the x there instead of that. But I mean, the answer has got to involve e. And if you think about it, it's probably got to involve e to the negative x squared if it's going to work. But is that right? Notice I purposely put a little space there. No, it's not quite right, but it's almost right. Check it by differentiation and see how far off you are. Take the derivative of this. Use the chain rule. Get an extra factor of negative 2x. It almost matches that function there, doesn't it? Except for that pesky negative 2. Well, compensate. Put a negative 1/2 here. That'll work. There we go. Don't forget your plus c. That works. Guessing worked. Will it always work? No. Will it sometimes work? Yes. Will you get better with practice? Yes. Is there a systematic way to do this that doesn't involve guessing? It depends on what you mean by guessing. There is a somewhat systematic way to do this, but it still involves guessing to some degree. You say to yourself, boy, if that were just e to the x, that sure would be nice. It'd be easy. It's not e to the x, it's e to the negative x squared. And there's also this pesky x in front. But maybe I should just introduce a new variable. I'll call it w. To be the thing that I'd like to be, a plain old x, but it's not. And if I do that, can I just go ahead and replace that negative x squared with w and be done with it? What in the world am I doing? Okay, what I'm about to show you is mysterious. And I'm not explaining it, that's for Wednesday. But it is the technique. We're not going to stop there. We need to bring in the negative 1/2 somehow. And the way you get that is by differentiating this with respect to x here. And then pretending this is a fraction. Multiply both sides by dx to get dw. Hey, Arthur, equals negative 2x dx. Sorry. Okay, dw equals negative 2x dx. And then I got an x dx in there. There's an x dx. Divide both sides by negative 2. X dx is negative 1/2 dw. So put that up there. Put the negative 1/2 here and the dw there. Weird. What will this be? That's an easy integral. Negative 1/2 e to the w plus c. But wait a minute, we're not done. The answer's got to involve x. Replace w with negative x squared. We got the same answer. Magic. What in the world is this? It's substitution. Is it magic? No. Just feels like magic. We will explain it on Wednesday. It is the main subject of section 7.1 in the book, starting chapter 7 here. We need more practice and more explanation. We're not done. Hang with me here. We still need to find the mass. We need to integrate from 0 to 2. Now use the fundamental theorem of calculus. We don't need the plus c. We're doing a definite integral. Now when I plug in 0, I do not get 0. E to the 0 is 1. Two negatives make a plus 1/2. I get a 1/2 minus 1/2 e to the negative 4. For the mass, that would be in grams. It turns out to be approximately 0.4 something. Let's see, 0.5 minus 0.5 times e to the negative 4. It's about 0.491 grams for the total mass of the thin rod based on this mass density. Yeah, this mass of a thin rod kind of thing might seem like a phony application, but it's still good to learn about. Comes up in mechanics, but my interest ultimately is more about probability and statistics. And this kind of idea of a density function is really useful in probability and statistics. My personal thing that I want to focus on a lot.